In this video, I'll show you how to go about differentiating natural logs, which you'll see is sort of similar to differentiating Euler's number, or at least it's certainly related. So we'll start with looking at the proof. Okay, how we go about this. So to look at the proof for the derivative of a natural log, you want to start with y equals ln kx. Okay, so natural log of some function kx. Now the first thing we're going to do is solve for x. So we need to extract x out of there. And of course the way we do that is by using the fact that this is log of natural log of e, log base e. So then we can rewrite this as e to the power of y equals kx. Now, if you're a little bit rusty on your log laws, because that was last year, and you need to brush up on that, then do go back and make sure that you're comfortable with converting from this form, this linear form or logarithmic form, into exponential form. So that's where we start with. Now we want to get x by itself, and we're going to say x is 1 over k times e to the power of y. Okay, so far so good. Now we're going to differentiate this, but instead of being dy dx, we're going to do dx dy, which is just saying that we're differentiating this with respect to y, whereas usually we do it the other way around, because usually we have the y by itself. But it's the same process. So dx dy. Alright, and we know from our previous video and our work with Euler's number that the derivative of e to the y, or e to any variable, is just itself, and this constant will stay unchanged. So we're just going to have 1 over k e to the y. So the derivative of this is itself. We know from back up here that e to the y is kx, so what we end up with is kx over k, and of course those cancel out, leaving us just with x, but we don't want dx dy, we want dy dx, so we can actually just flip that upside down. dy dx, which gives us 1 on x. So the derivative of y equals natural log of kx is just 1 on x, and it doesn't matter what this number is in front here. That could be 5 or 10 or 368 million. It doesn't matter. It's still 1 over x. Okay, so in general, we say that if your function is ln of kx, where k is greater than 0, then the derivative is just 1 on x. So this k kind of drops out of circulation. We don't need it. It doesn't affect the derivative. Alright, so let's have a very quick look. Now, if you're not convinced, you can actually use the chain rule to do this. So if you're comfortable with the fact that if y is ln x, then y prime is 1 on x. Okay, so if we use that, we can use the chain rule to prove that this 5 isn't going to come into it. Okay, so let's say let u equal 5x. Therefore, we have y equals ln u. Okay, now the chain rule gives us that dy dx is dy du times du dx. dy du is just, over here is just 1 on u. Okay, and du dx, which is this one, the derivative of 5x is just 5. Okay, going back up here, u equals 5x, so that gives us 1 on 5x, times 5. Okay, those cancel out, gives you 1 on x. So hopefully that proves to you, so that you're comfortable with the fact that this, whatever the constant here in front of the x is, doesn't make any difference. It still gives you 1 on x. Now it does change a little bit if we have a horizontal translation in there. So if we add a constant plus b in here, then it does look a little bit different. So what we end up with is that for this case, and providing that minus b on a, x is greater than minus b on a, which is basically just saying that's not 0, then we have dy dx is a over ax plus b. Okay, so it's essentially the derivative of what's in the brackets, that's a, divided by whatever's in the bracket. Alright, so again we can look at this with the chain rule. So for this one we're going to say let u equal 5x plus 3. Okay, we're doing the same thing. So y then equals ln u. dy dx is going to be the derivative of y with respect to u, which is 1 on u, times the derivative of u with respect to x, which again is just 5. Okay, but this time, because u is all of this, it won't cancel out with the 5, so what you end up with is 5 over 5x plus 3. Okay, so you can see that the derivative of whatever's in the brackets, which is just 5 at the top, divided by 5x plus 3 as your denominator. Okay, so what about negative x? What if we had ln negative x? So again, we can do this with chain rule. If we let u equal minus x. Okay, and again, then we have y equals ln u. And therefore, y prime is the derivative of that, 1 over u, times the derivative of u with respect to x, which is minus 1. Okay, u is minus x, so we have 1 on minus x times minus 1, which of course just gives us 1 on x. So it is actually the same. So it doesn't matter if x is positive or negative. In this case, you still end up with 1 over x. So hopefully again you can see that how handy the chain rule is in proving these sorts of these results, and that you really need to be fluent with it. Okay, so if we want to generalize, we're going to say let some function h of x equal ln of some function of x, okay, and what the derivative then ends up being is your derivative of the function, like I said, derivative of whatever's in the brackets, divided by the function that's in the bracket there. Okay, so that's how we generalize that. So that means once we start putting sort of more curly kinds of things in here, other than just straightforward polynomials, you can still do the derivatives of the natural log there. Okay, a couple more examples just to finish off. So again, differentiating with respect to x, now we're using our nice little rule that that's going to be f prime x over f of x, where whatever this in the brackets is f of x. Okay, so for a, derivative, so if y, if y is ln x squared plus 2, then y prime will be the derivative of what's in the brackets, 2x, divided by the bracket itself, x squared plus 2. Okay, and for b, is slightly more complicated because this involves the chain rule, x squared, so what we're going to say is let u equal ln x, okay, and then what you have is u squared, which means the derivative is going to be the derivative of this, 2u, okay, times the derivative of that, which we know is just 1 on x. Alright, we know that u is ln x, so we have 2 times ln x on x, and that's your derivative there. So that's all there is to differentiating natural logs. Just remember that if you've got whatever your function is in the brackets, whether it's just x or 3x or some quadratic, whatever, then using the chain rule to prove that you, to differentiate it, you have f prime x, so derivative of whatever that is, divided by the original function there. So hopefully you can see that that sort of has some relation to what we were doing with Euler's number before.